Just like we defined a row space as the span of the rows, we can define the column space of a matrix to be the span of the columns. And we'll write that like this, call A. Note that if our matrix has m rows and n columns, then each column has m entries in it. And so the column space of A will be a subspace of Rm. And then in analogy with row space and row rank, we can define the column rank of a matrix as the dimension of the column space. So I guess we could write C rank of A is the dimension of the column space of A. Okay. Now, we have no reason to believe that the column rank has anything to do with the row rank, so careful there. And also, we've been doing a lot of row operations. We have to be aware that row operations, they don't change the row space of a matrix, but they can change the column space of a matrix, right? So, as an example, just to take one obvious example, if we have this matrix, right, the column space of this is just the span of 1, 1, right? Well, if we do row 2 minus row 1, we end up with 1, 1, 0, 0. And now the column space of this matrix is the span of the single vector 1, 0. Right? These are clearly not the same subspaces of R2. So this row operation has changed the column space. This is kind of unfortunate because, right, we're used to doing row reductions. So if we want to find a basis for the column space of a matrix, we can't do row operations. Well, we have a couple ways of fixing this. One is, instead of doing column operations, instead of doing row operations, do column operations and reduce it to column echelon form. But rather than trying to figure out exactly what that means, right, we can just turn so to find the column rank of a matrix, find the basis of the column space, we can just turn these columns into rows and then do the usual row reduction. When we're done, we just have to remember to turn our vectors back into columns at the end. So what we can do is replace this matrix with its transpose. Okay, so this superscript, this means transpose. And the transpose of a matrix is you just turn each row into a column, which will also turn each column into a row. Right? Another way to write this is that if A is the matrix with entries ij, then A transpose is the matrix with entries aji. I think it's easier to understand what transpose is if you actually just do it and look at an example. So here's what the transpose of this matrix looks like. I've got it tucked down here somewhere. So here's A transpose for this particular matrix. You can see that each column here, so this first column becomes the first row of the transpose, second column of the original becomes the second row of the transpose, and so on. And then similarly, the first row of the original is the first column of the transpose, second row of the original is the second column of the transpose, and so on. All right, so here's the transpose. Now, of course, we had a question about the column rank of the originals, so we needed to know about the column space of A, but the columns of A are the rows of A transpose, so the column space of A is going to be the row space of A transpose. So we can work with the row space of A transpose, and we know how to do that. You just do row reduction, right? Which we know how to do. So I won't drag you through the row reduction, but this is the result. This is the reduced row echelon form you get after you do row reduction. So the basis for the row space of A transpose is just these rows, 1, 0, minus 4, 0, the non-zero rows, I should say, and 0, 1, 3, 0. Okay, so to get a basis for the column space of A, we can just take the transpose of these, which gives us column vectors. So turn these back into columns, essentially. 1, 0, minus 4, 0, and 0, 1, 3, 0. All right. So here's the basis for the column space. Now remember, the original question was to find the column rank of A. Well, this is the dimension of the column space of A, but we have a basis for the column space that has two vectors in it, so the dimension of the column space is 2.